Welcome learners. In our lesson today we look at nitrogen and its compounds. Subtopic is nitric pipe acid. We look at laboratory preparation, industrial manufacture, chemical properties and uses. Now first we look at laboratory preparation of nitric pipe acid. Reactions used: potassium nitrate, concentrated sulfuric 6 acid. Reason for using potassium nitrate: it does not contain water of crystallization. Now condition requires gentle heating. Reason for gentle heating: to minimize thermal decomposition of nitric pipe acid. Equation: potassium nitrate, sulfuric 6 acids, arrow, nitric pipe acid, potassium hydrogen sulfate. Type of apparatus used: it should be made of glass only, that is retort flask is used. Reason: nitric pipe acid is corrosive, hence attack rubber and cork. So the diagram below shows laboratory preparation of nitric pipe acid. So the mixture, this is potassium nitrate, that is concentrated sulfuric acid. The mixture is gently heated in a retort flask. And then the nitric pipe acid is formed here. It appears as brown fumes. It is collected on this other side, condensed by the tap water, so you form here nitric pipe acid. Points to note: the nitric pipe acid fumes are brown. Reason: due to presence of nitrogen 4 oxides formed by thermal decomposition of nitric pipe acids, as by the equation below. Nitric pipe acids, arrow, nitrogen 4 oxides plus oxygen plus water. The nitric pipe acid collected is yellow in color. Reason: due to presence of dissolved nitrogen 4 oxide gas. How is the yellow color removed? By boiling air through the acid. An acid salt is formed during the preparation of nitric pipe acid instead of a normal salt, which is potassium sulfate. Reason: the formation of a normal salt requires high temperature that cannot be achieved in a classroom situation. Now next to look at is industrial manufacture of nitric pipe acid. It's done by a process called Oswald process. It relies on catalytic oxidation of ammonia gas. Raw materials include ammonia, air and water. Optimum condition: temperature of 900 degrees Celsius, pressure of 9 atmospheres, catalyst platinum rhodium. Parts of the process includes purifier, compressor, heat exchanger, catalytic chamber, reaction chamber, absorption tower. Now function of each part. First part is purifier. Role: remove impurities, e.g. dust particles. Reason for removing impurities: prevent poisoning of catalysts. Part number 2, compressor. The ammonia air mixture is compressed, that is volume is reduced. Reason: so as to raise the pressure of the mixture to about 9 atmosphere. Heat exchanger. Role: is used to preheat the ammonia and air mixture to about a temperature of 230 degrees Celsius. That is, the reason for that is so that it attains suitable reaction temperature. Another function of the heat exchanger is used to cool nitrogen 2 oxide gas formed. Next part is catalytic chamber. The temperature of the ammonia and air mixture is raised further to about 900 degrees Celsius, then passed over heated platinum rhodium catalyst, where ammonia gas is oxidized to nitrogen 2 oxide gas and water. Equation: nitrogen ammonia plus oxygen, arrow, nitrogen 2 oxide plus water. Balance the equation: 4 wedges ammonia, 5 wedges water, 4 wedges nitrogen 2 oxide. To balance the equation, place 4 wedges ammonia, 5 wedges oxygen, 4 wedges nitrogen 2 oxide and 6 wedges water. Reaction chamber. Now in the reaction chamber, nitrogen 2 oxide is further cooled to a temperature below 45 degrees Celsius, so that nitrogen 2 oxide is easily oxidized to nitrogen 4 oxide. So the equation, the reaction chamber is nitrogen 2 oxide plus oxygen arrow nitrogen 4 oxide. Balance the equation, place 2 where there is nitrogen 2 oxide and 2 where there is nitrogen 4 oxide. And the last part is absorption tower. A mixture of nitrogen 4 oxide and nitrogen 2 oxide is passed up the absorption tower against a downflow of hot water, where nitrogen 4 oxide and water combine to form nitric 5 acid and nitric 3 acid. Equation: nitrogen 4 oxide plus water arrow nitric 5 acid HNO3 plus nitric 3 acid HNO2. Balance the equation, place 2 where there is nitrogen 4 oxide. The nitric 5 acid, the nitric 3 acid formed is oxidized to nitric 5 acid by excess air. Equation: nitric 3 acid plus oxygen arrow nitric 5 acid. Balance the equation, place 2 where there is nitric 3 acid and 2 where there is nitric 5 acid. Note that the unreacted nitrogen 2 oxide and air are recycled to the compressor so as to minimize wastage and also to reduce the cost of production. Now, another point is about to note is the nitric 5 acid obtained by this process is 65% pure, that is contains 35% water. How is concentration increased? Concentration is increased by careful distillation of the solution over concentrated sulfuric acids that act as a dehydrating agent. So the flow diagram below shows industrial manufacture of nitric 5 acid, where I said the raw materials, air and ammonia in the first part, which is the purifier, where they remove impurities, dust particles, then pump the compressor where it is compressed to raise the pressure, and then the heat exchanger where they are preheated to a temperature of about 230, that is to attain suitable reaction temperature, then pumped catalytic chamber where it is further heated to 900 degrees Celsius and passed over platinum rhodium where nitrogen 2 oxide and water are formed. The nitrogen 2 oxide is pumped back to the heat exchanger for cooling. Then the nitrogen 2 oxide is pumped to the reaction chamber where air comes in, purified air. Nitrogen 2 oxide is further cooled to about 45 degrees Celsius so that it is easily oxidized to nitrogen 4 oxide. From the reaction chamber, the nitrogen 4 oxide and nitrogen 2 oxide unreacted is pumped to the absorption tower where you bring in hot water. The react with nitrogen 4 oxide to form nitric 3 acid and nitric 5 acid, where the nitric 3 acid is oxidized to nitric 5 acid, so you get about 65% nitric 5 acids, and reacted nitrogen 2 oxide is recycled back to the compressor. Now, the physical properties of concentrated nitric 5 acid include it is a colorless fuming liquid. It has a boiling point of 83 degrees Celsius. It has a percentage purity of 68%. It has a density of 1.42 grams per centimeter cubed. Chemical properties of concentrated nitric 5 acids. 1. Reaction with acidified iron 2 sulfates. Equation: 6 iron 2 sulfates plus 3 sulfuric acids plus 2 nitric 5 acids arrow 3 iron 3 sulfates plus 2 nitrogen 2 oxides plus 4 water. Observation made when concentrated nitric 5 acid is added to acidified iron 2 sulfates. A pale green solution changes to yellow. Reason: concentrated nitric 5 acid oxidizes iron 2 ions to iron 3 ions while itself reduced to nitrogen 2 oxide and water. Observation number 2. Brown fumes of nitrogen 4 oxide are formed at the mouth of the test tube. Reason: the nitrogen 2 oxide gas formed is oxidized by air at the mouth of the test tube to form brown nitrogen 4 oxide gas. Chemical property number 2, reaction with metals, e.g. copper. Chemical equation: copper plus nitric 5 acid, arrow, copper 2 nitrates plus nitrogen 4 oxide plus water. To balance the equation, place 3 where there's copper, 8 where there's nitric 5 acid, 3 where there's copper 2 nitrates, 2 where there's nitrogen 4 oxide, 4 where there's water. Observation made when concentrated nitric 5 acid is added to copper tannings. Brown copper solid dissolves in the acids. A green solution is formed. Brown fumes are formed. Reason: concentrated nitric 5 acid oxidizes copper to copper nitrate solution while itself reduced to nitrogen 4 oxide and water. The next chemical property, reaction with nonmetals, e.g. sulfur. Equation: sulfur plus nitric 5 acid, arrow, sulfuric 6 acid plus nitrogen 4 oxide plus water. To balance the equation, place 6 where there is nitric 5 acid and 6 where there is nitrogen 4 oxide, 2 where there is water. Observation made when concentrated nitric 5 acid is added to sulfur. A yellow solid dissolves in the acid. Brown fumes are formed. Reason: concentrated nitric 5 acid oxidizes sulfur to sulfuric 6 acid while itself reduced to brown nitrogen 4 oxide gas and water. Now, physical properties of dilute nitric 5 acid. It changes blue litmus paper red. It conducts electricity due to pressure of free and mobile ions. Chemical properties of dilute nitric 5 acid. This one behaves like a typical acid. Reaction with bases. It forms metal nitrate and water. The reaction is called neutralization reaction. Example: copper 2 oxides plus nitric 5 acid, arrow, copper nitrates plus water. Reaction number 2, reaction with carbonates. When carbonate is added to nitric 5 acid, it forms a metal nitrate, water, and carbon 4 oxide. Observation made during the reaction: effervescence occurs. Reason: due to production of carbon 4 oxide gas. Example of a reaction: equation: zinc carbonates plus nitric 5 acid, arrow, zinc nitrates plus carbon 4 oxide plus water. Balance the equation, place 2 with the nitric 5 acid. Lastly, reaction with metals. Dilute nitric 5 acid does not produce hydrogen gas with some metals as expected. Reason: nitric 5 acid is a strong oxidizing agent, hence oxidizes hydrogen gas formed to water. Uses of nitric 5 acids: manufacture of fertilizers, manufacture of explosives, manufacture of dyes and drugs, etching designs on some metals. Learners, that is the end of the lesson. In the next lesson we will look at fertilizers.